My name's Daniel Situnayake. I'm going to be your host today. So before we get going, I wanted to talk about our sponsor, Edge Impulse. So Edge Impulse is the company that I work at. So I'm a little bit biased, but I think it's the easiest way to get started with embedded ML. So you should definitely check out edgeimpulse.com. And thank you very much to Edge Impulse for sponsoring this talk series. Our next talk is going to be on Tuesday, June 9th. And we have two more awesome presenters. We've got a presentation on sparse architecture search for CNNs on resource-constrained microcontrollers by Igor Fedorov, and a talk from Dominic Binks on tinyML doesn't need big data, it needs great data. So this is going to be 8 AM Pacific, same time on Tuesday, June 9th. So our first talk today is from Laszlo Kindrat from XMOS, and the title is Low-Cost Neural Network Inferencing on the Edge with xcore.ai. So Laszlo is currently in the role of machine learning engineer at XMOS in Hampton, NH. He has aided the design of the XS3 architecture's vector unit and plays a key role in developing inference tools for the xcore.ai platform. Laszlo has experience with traditional and machine learning algorithm development, and he holds a PhD in applied mathematics from the University of New Hampshire. So I'm going to switch over to Laszlo's slides now. If you have any questions during the talk, please use the Q&A feature of the platform to ask them, and I'll be able to relay them to Laszlo after the first part of his presentation.
Thank you, Daniel, for the kind introduction. And I would also like to thank the organizers for enabling us to present our work here. Let me bring up my slides. So in case you haven't heard of XMOS before, we are a fabless semiconductor company based in Bristol in the United Kingdom. And our next chip called xcore.ai has just been recently back from the foundry. And today I would like to talk to you a little bit about this chip and some of the design choices that we made to make this a good choice for your edge AI applications. And also I would like to demonstrate a little bit on how we imagine neural network model deployment on this platform. So let me kick off by giving you a bird's eye view of the chip's architecture. Our chip consists of two tiles, and you can think of a tile as something similar to a traditional processor core. Each tile, you can see one here on the right and one on the left, has 512 kilobytes of RAM, and it has an arithmetic and logical unit, including a floating point unit and a vector unit that I'm going to talk a little bit more later on. What makes it special, and this is actually our own architecture at XMOS, is that each tile has what we call 8 logical cores. And you can think of a logical core as essentially a hardware implementation of a thread. So each logical core has its own register files, scalar as well as vector registers, but they share the ALU. Now these cores can execute simultaneously, and we give you hard real-time guarantees. So this is actually a very good choice if you have an application that requires hard real-time guarantees such as audio. Now this architecture gives you a couple of advantages. First of all, these cores can be programmed to do pretty much anything you want. And in particular, one thing you can do with them, you can use them to implement hardware interfaces in software. And that's in fact what we do. And this is the first design choice that allows us to keep the cost low, since we don't have to design or license hardware IP. The second thing is you have a lot of flexibility here, and you can use this essentially as a small SoC. You can run an instance of FreeRTOS, which we have recently ported to our platform, but you can also run a far-field microphone array. You can interface with a camera, and most importantly, for the context of this talk, you can run neural network inference on it. Of course, there are other decisions that went into making this chip efficient and cheap, and one of them is the process node. So it's important to choose a process node that keeps the chip small and easy to manufacture. But what I'd like to talk to you about next is actually a little bit on what were the decisions behind this vector unit. And this vector unit, it's really quite different from what you would see in a traditional RISC architecture. First of all, it's very wide. The vectors are essentially 256 bits that are contiguous in memory or in one of our vector registers. And these vector registers have single cycle memory access. This actually means that this vector unit doesn't really have much overhead when it's trying to access data that's in your processor. And this further gives you some performance. It also keeps your whole system design potentially simpler, since you don't need an external accelerator. And you also are able to reduce the latency, since whatever data you want to operate on with this vector unit, it's immediately available. In RAM, you don't have to offload it to a coprocessor. Now, this vector unit can be configured. It can operate inside 8, 16, 32-bit modes, as well as binarized mode. And that's actually one direction we think has a lot of potential, namely binarized neural networks for particularly edge AI applications. I mentioned this vector unit is not like traditional RISC architectures, and one of the reasons why it's very different is that most of the instructions actually perform a load from memory and some arithmetic operation. And I'm going to illustrate this in a bit by showing one of the instructions in detail. We have decided to, in parallel with this vector unit, dual issue some other instructions. And this basically means that while you're executing your arithmetic operations that perform the dot products and the matrix vector operations for your inference, in parallel, there are instructions that take care of your pointer math. So you can advance your indices when you're calculating a convolution or matrix vector multiply. And these two, as well as with some other novelties, allows you to have very long sequence of essentially multiply accumulate instructions. And that's how we can give you high arithmetic density, which is important if you want to be efficient. Now on the left here, you can see a little illustration of one of our instructions, which is very representative of what kind of ideas we have in this vector unit. So this VLMAC R, or vector load, multiply, accumulate, and reduce, first performs a load from memory, so loads 256 contiguous bits, and calculates the dot product of that with a set of essentially coefficients, but you could think of it the other way around, that you load a set of coefficients and you stored a set of data in your register. Either way, what you get is a dot product of coefficients and data, which then you put into an accumulator. Now, this already makes it relatively efficient. However, we go one step further. We implemented a hardware ring buffer, which allows you to not have to store the result of this dot product immediately, but instead just keep on going and doing multiple dot products in a row. And eventually, once you have calculated the dot products that you wanted, they are going to appear in this ring buffer and you can store it off to memory. So before I go on to the demo, I'd like to give you a little overview of what infrastructure we use to deploy neural networks. And we have decided to go with TensorFlow Lite for microcontrollers, of which you, if you follow this webinar series, have heard before. Basically, the workflow would start with either you train your own floating point neural network in TensorFlow or some other framework, or you download one of the pre-trained ones. And as long as you can convert it to TensorFlow format and you can push it through the TensorFlow Lite converter and quantizer, our workflow will work for you. So once you have quantized and converted your model using the built-in quantizer converter, we provide you with a standalone tool that performs the platform-specific transformations and optimizations on your model. Now, this tool directly operates on the TF Lite models, and it outputs another TF Lite model with some custom operators in it that you can then deploy in our port of the TF Lite micro runtime. With that, we also provide a kernel library, which is, by the way, a standalone product. So if you ever decide that you want to write your own runtime or something like that, you can do that. So before I go on to the demo, I think this would be a good time to answer some of the questions from the audience. Daniel?
Great. So if you have any questions, please post them in the Q&A section of Zoom, and I'll be able to read them out. And in the meantime, I've got a couple of questions that I wrote down. So I was wondering about, Laszlo, what do you think some typical applications are for your platform?
Excellent question. So we have had a lot of experience in the past with far-field audio. And in fact, we currently have products for that space. So that would definitely be an application. I didn't mention it, but our vector unit also has instructions that were designed specifically for fast Fourier transforms. So for those applications, we can be really performant. Now, the demo I will show you is a kind of lightweight image classification, and we can perform that as well. And our chip has a MIPI interface, so you can interface with the camera directly.
Fantastic. Okay, we've got a ton of questions now. So here's a good question from Joe Hoffman. Can you give further insight on the mapping process? It seems like there could be millions of transformations, and how does XMOS find the most efficient implementation?
Great, so let me go back just a slide. So the question here is basically what's inside this box, which converts a TensorFlow Lite model to something more optimized. And really what we started with is trying to find the most efficient ways to implement convolutions and fully connected layers and other typical operations for our platform. We implement these in assembly and make sure they're really performant. And then essentially the job of this box is what you would typically think of as a compiler. That is to take the sort of vanilla TensorFlow Lite model and perform specific graph transformations, which could be fusing, splitting, replacing certain operators with others that are that make it more make it faster or more memory efficient on our platform. And really the typical operator, the typical operations are what you would see in a compiler. Very similar.
Okay, great. So a question from Jake Pan. So do you support both floating point and int8 in the inference?
So we run TensorFlow Lite for microcontrollers. So if you have a floating point model, it will work as long as the micro runtime has the appropriate floating point operators registered. Our vector unit is only for assigned 8, 16, and 32-bit integers. So if you want to take advantage of the vector unit, then you would have to quantize your neural network. But obviously you have a choice what bit depths you choose there. We recommend int8.
So question from Ravi. Not sure if this was covered, but is there a throughput number, e.g. TOPS or inferences per second on a reference network?
I will show you an example in the demo, and there will be some timing there, and I'll explain the caveats. What I can tell you right now is the theoretical maximum of the whole chip is 50 gigamax per second. In practice, you wouldn't get that, and also this chip in most applications would be used, as I said, a little more like an SoC. So a lot of other tasks would be running on it. Now we have at the tinyML Summit published some numbers on a network that was openly available.
Very good question from Rafal. What is the typical power consumption during inference?
Sure. So as I said, the chip just recently came back, and we haven't fully characterized it yet. So without giving you any specific numbers, what I can tell you is the peak power consumption if you try to run this at the theoretical maximum utilization of the VPU, which, as I said, is not a reasonable scenario. It's in the 1 to very few hundred milliwatts.
Okay.
Now, with the caveat there that you can clock this device down, and this is at 700 megahertz.
All right, thanks, Laszlo. So we have plenty more questions, but we will be able to get to questions in the forum afterwards and post some answers to the ones we weren't able to get to now. But I will let you continue with the next part of your presentation.
Sure, thank you, Daniel. So I'm gonna switch to the demo. And what I've decided to do here is just give you a kind of idea of how this, how that workflow that I showed you looks like in practice. And I'm not going to go into detail very much on what's happening under the hood. What I really want to do is just show you what would be the steps if you were a customer of ours and you'd want to deploy on this device. So I picked a variant of MobileNet, and as you can see here, it's with alpha equals 0.25. And the only thing I'm gonna do to this is I'm going to restrict the number of classes to 10. Obviously, in your application, you would probably want to retrain, or probably you bring your own architecture. But for the purposes of this demo, this will work. And as you can see, it's just the kind of off-the-shelf MobileNet with a dense layer that outputs 10 predictions instead of 1,000. And what I want to highlight here is this model has 220,000 weights. So what we can expect after quantizing it to signed 8-bit integers is that the model size should be around 220 kilobytes plus some overhead. I prepared some example data so that we can do the quantization, and there are really no surprises here, just 10 examples of each of the first 10 classes. And before I move on, I'm just going to run inference on these using the floating point model in Keras, just so that we see what this model outputs for these 3 example images. And the next step in your deployment process would be to quantize this. And of course, if you want to do it, you can do quantization aware training and kind of skip directly to the quantized network. But this would be a typical workflow. So if you want to quantize a pre-trained floating point network, we give you essentially helper functions that wrap around the built-in quantizer converter. And it's really just so that you don't have to worry about the exact settings of the quantization that are required for xcore.ai. So really it's just a couple lines of Python, and what it will give you is a quantized model that you can then, using the built-in interpreter, evaluate. And what you can see here is that for the goldfish and the ostrich, you have a little lower prediction probabilities, and then for the hammerhead, it's actually quite a bit off. And you could mitigate this effect, as I said, either by quantization-aware training or just training it properly on the classes that you actually want to classify on. Now, so far there isn't really anything platform specific. The next step would be to optimize this for xcore.ai. But before I do that, I'm going to save this network, and I'm going to visualize it, because I want to give you a few ideas about what's happening under the hood. Just a few hints. So this visualization tool, it's based on something that comes with TensorFlow Lite, and we have made a few improvements on it, and you could use different visualization tools that are perhaps better. This is actually really useful if you want to inspect what's actually in the TensorFlow Lite flat buffer file. And what I want to point out first is that this model that, again, just came out of the built-in converter is 320 odd kilobytes. So there's a significant amount of overhead, or so it seems. And if you inspect this model, what you will see is actually there's a lot of information about the different tensors in this model. And in particular, there is a lot of information that describes how they are quantized. And I'm just going to go through this to give you an idea how many quantization parameters you can see here. By the way, you can also see that the names of these tensors are relatively long. They're not necessarily human readable, or at least they might not give you the best ideas of where these tensors are located. So once you go through all of these, and there are a lot of them, I think close to 100, eventually you can see the list of operators that are also in this model. And finally, the visualization. And really what I want to point out here is, if you're familiar with the MobileNet architecture, in V1, some of the depth-wise convolutions are preceded by an asymmetric padding. This is not something that the built-in depth-wise convolution converter the built-in depth-wise convolution operator is capable of implementing by itself. So it will appear explicitly as a padding operator. And back to the question, what are the optimizations that our platform does? This will be one of them. We can actually perform convolutions with arbitrary input padding. So before I go back to the notebook, I just want to point out that actually, if we just look at the parameters which are stored in these buffers, essentially these are the data structures that stored in numerical values for weights and biases. You can see that it is around 220 kilobytes, and the overhead that comes from describing the architecture and metadata is around 32-3%. So once you have that, and perhaps you're happy with your quantized model, we give you a converter, it's just a simple function that you pass in your quantized model, and out comes a xcore optimized quantized model. And to be able to evaluate this without having to actually run it on the device, what we decided to do is to implement Python bindings for an interpreter that essentially runs a TensorFlow Lite for microcontrollers runtime on your host with reference implementations of our kernels. This means that you can get bit perfect outputs in terms of what would be the output of the actual device. And what you can see here is we have results for the goldfish and the ostrich, which are indeed bit perfect to what the quantizer would give you straight away. And then with the hammerhead, we have a slight deviation from what the quantizer gives you. And this can happen. Our hardware implements different saturation and rounding rules than what the reference operators would do. But typically the result is very, very close. So once you have that, you can also visualize this network. And as you can see, the file size actually has gone down significantly. It's not at 220 kilobytes yet, but I'll explain that in a moment why. You can see that the tensors no longer have all that quantization information. And again, I'll mention that in a moment again. They have a little nicer names, and these names can be shortened further. In fact, I think on this model, you can save an additional something like 5 kilobytes just by making these even shorter, which might matter if your application is really memory sensitive. We also reduced the number of tensors. I think it's 90 instead of 99 in this particular case, as well as the number of operators. And as you can see, now a bunch of platform-specific operators, starting with XE underscore, have appeared. And you can also see that the explicit paddings no longer appear. Now, before I move on and talk a little bit about the parameters, I want to point out that our platform has word-aligned memory addressing, which means that actually it's much more efficient to have input images that have 4 channels rather than 3. So we do an explicit padding in the channel direction. And this is something, again, that's platform specific, and our optimizer does this. But if your images come from our MIPI interface, this operator actually can be done by that MIPI interface. And in that case, the converter can be configured so that it won't do this explicit padding, at least not in the micro runtime. And finally, I just want to show that the buffers have actually grown a little bit. And this is because we take those quantization parameters and we pre-calculate some tensors that you would typically have calculated at initialization or prepare time by the runtime. So peak memory usage actually doesn't change, but you have shorter init time, and these things are calculated by the host rather than the device. So with that, I am going to show you how our device works right now. And basically what we've done here is we've taken this MobileNet model and we've wrapped it in an application. And in your particular application, you would put other things in there, obviously. For example, you would run FreeRTOS, a Wi-Fi stack, other interfaces, and so on. But right now, I just started this, this program on the device, and it's listening and it's waiting for me to send some images there. And all of this is happening through a debugger right now. So the first image takes a little bit of time. There are some handshakes that happen there. But once it's sent to the device, you can see that some numbers come back. Let me start in the end, that indeed the prediction is bit perfect to what we've seen. It was 46.48% for the hammerhead. And then we also have some timings, and just to prove that this isn't something I set up earlier, I can run the same thing on the goldfish, and we should have same results. The timing should be the same. Again, we have a hard real-time guarantee here. And one of the previous questions asked about timing. Here, the total time is 18 milliseconds. However, about 8 milliseconds of this is due to the printing that's happening here. In practice, this model would run on around 10 milliseconds. And with that, I'd like to thank you for your attention and the opportunity to talk here. And Daniel, I'm ready for more questions.
All right, thank you so much, Laszlo. That's really interesting and sounds like an amazing piece of technology. So a question that we have from a lot of people is, how soon will eval boards be available and how much are those going to cost?
Okay, so the first customer samples and dev kits will be available late summer this year. And for exact pricing, I recommend you get in touch with our sales department.
More questions. So how do, given you've got 512K of RAM, that's only enough for a small model. Can the model execute from Flash, and how big is the Flash?
Mm-hmm. So not only can it execute from Flash, we also have an external DDR interface. I'm not entirely sure how big the Flash will be on the devices that we will actually sell, but you can definitely execute from those.
Okay, fantastic. So from Anuj, is this chip generalized? Can it run CNN or RNN or other types of architectures, or is it only good for some architectures?
So you can run anything you want on it. The vector unit is more efficient if you run on CNNs or some other type of network where the weight reuse ratio is high. But there is nothing to prevent you from running any model in the current workflow, as long as you can convert that to the TF Lite format and it fits in internal or external memory.
Okay, thank you. And from Hiroshi, is the core of XCore a totally new CPU architecture or based on some existing one?
Yeah, so the instruction set architecture is ours. It's not based on ARM or some other well-known architecture. It is not totally new because this is our third generation, and the architecture is actually called XS3 because of that. And you can buy actually dev kits with the current generation chips. And really what happened is we built on top of that architecture and we added the vector unit and the floating point unit. But it's proprietary and it's our own. Okay,
a question from Ram. Do each of the logical cores have an ALU which includes a multiply accumulate unit?
That's a great question. So each tile has an ALU and the cores share it, but they can use the ALU at the same time. And the way that's implemented is we have a 5-stage instruction execution pipeline, which means that at any given time, any 5 cores you have can execute an instruction.
Okay, great. And so does your converter perform quantization, or is it the user's responsibility?
So the converter itself, that blue box, doesn't perform the quantization. What performs the quantization is the built-in quantizer converter, and we give you helpers for that. So it wouldn't be a big deal if that's something you want. We can wrap the two things in one. So instead of two function calls or 2 lines of Python, you can do it in 1 line.
Okay, great. And so another question, what is the size of the TensorFlow runtime?
Mm-hmm. So it really depends on how many operators you register in it. I think for this particular application, it's something around 100 kilobyte, but that might include some other things as well. It can be as low as 20 kilobytes, and it can be very high if you register all our custom operators and the built-in ones. The built-in ones in particular can take up a lot of space. And what we are working on, and I believe the TF Lite micro community is also working on this, is to give you the ability to automatically pick the operators that your model would need and register only those, so that you can manage the overhead by the runtime.
Awesome. And I think final question, does this chip support LSTM?
So currently the TF Lite micro runtime does not support LSTMs, as far as I know. There's, again, under an LSTM is just linear algebra and some activations, and we can speed those up. And the moment a reference implementation will be upstream to TensorFlow Lite for microcontrollers, we will make sure that you can run it on our device, and we will look into how we can speed it up to be the most performant we can get on this chip.
Okay, so that's all the questions we have time for before our second talk. But thank you so much, Laszlo. This was fascinating and really great to get some insight into the work you're doing. You'll have hopefully the opportunity to interact with folks on the tinyML forums after this. So if you have any more questions, you can head to the topic there and post them. Okay, so closing slides. So another thank you to our sponsors, Edge Impulse. Probably the easiest way, in my opinion, you can get started using embedded ML. So please go and check it out. Our next talk is going to be on the 9th of June, 8 a.m. Pacific time. And it's from Igor Fedorov at our machine learning lab on sparse architecture search for CNNs. And Dominic Binks from Audio Analytic, talking about tinyML not needing big data, it needs great data instead. If you're interested in presenting yourself, please contact talks@tinyml.org and we'll work with you on that. Finally, just hope that you can tune in next time. Thank you so much to our speakers. And this talk is going to be available recorded on YouTube, and the slides will be available on our website. If you have further questions for the speakers, you can please let us know on the forum, and we'll have the speakers check those out. So thank you very much, and look forward to seeing you next time.